Thanks. Good morning, everyone. I'm John McCormack from Monash University in Australia, and our paper is about how you collaborate with an AI in a musical context, in particular an improvisational musical context. So I wanted to start with a bit of a provocation that AI is actually becoming creative. So many people may be familiar with this auction that happened in October last year. 3 French students basically auctioned off a work that they said was created by AI, and it sold for 40 times its estimated value of $432,500 US. Prior to that, Ross Goodwin released a film created by AI called Sunspring, which received a lot of attention and was shown in science fiction films around the world. Francois Pachet and his team claimed to have the first piece of music composed by AI through the Flow Machines software. And in 2017, the New York Times ran this article claiming that AI was changing how people are working with creativity, reshaping the building blocks of music and art. And I think maybe a lot of that is kind of overhyped, and the truth is more that AI is becoming a valuable creative collaborator. So in the context of our research, we're interested in music improvisation. And for music improvisation, we make several assumptions. First is that trust is the most important thing in a quality musical improvisation. That's trust in your partner, and trust giving you a balance between doing something known and being able to take risks, being able to put things out there and trusting in your partner that they're going to respond to them in the right way. So in a good improvisation, these things happen almost without thinking. And the most important thing that we were looking at was that there's musical communication clearly between performers, but there's also non-musical communication. And in a really good musical performance, the performers experience a sense of flow. So they lose track of time and their surroundings, and they're completely immersed in the music-making process. And of course, for human musicians, this happens naturally and intuitively, and if you're really good and really well practiced, it results in some phenomenal levels of human creativity. So the question that we asked is, how can musicians effectively communicate when one or more of them isn't human? So if your collaborative partner is an artificial intelligence, you lose a lot of that communication that human-to-human collaboration takes for granted. So in a standard human-to-human collaboration, you've got musical communication that's happening between performers, but you've also got non-musical communication that's happening. Now, if you replace one of the human performers with an AI, it's effectively a black box, you lose that extra musical communication. So we wanted to test 2 different hypotheses related to extra musical communication between the computer and the human performer. The first one is that communication from the human to the machine enhances the machine's capacity to generate appropriate and complementary output. And the second one was in the reverse direction. So from the machine to the human, that can facilitate a more engaging human-machine musical interaction. Okay, so before I talk in detail about the experiment itself and what we did, I wanted to talk about flow a little bit more, because this is one of the key measures that we use to understand how performers were collaborating with the AI. So there's been a lot of research that's shown that flow is a reasonably good proxy for musical engagement. There's been several large-scale studies over hundreds of musicians that demonstrate when they think the performance is the best, both from an audience and a performer perspective, that they're in flow states. Flow is characterised by cognitive, affective and psychophysiological indicators, so we can use a number of different measures to basically validate whether we think someone's in a flow state. And some of those psychophysiological indicators include heart rate variability, skin conductance, EEG, and there's several others that have been done as well. So the other important aspect of measuring flow is that, of course, it can be done post-performance through some kind of survey, and a commonly used survey for that is known as the flow state scale. So we indeed used this survey in the work that I'm going to describe in a minute. So Looking at prior work, probably the most obvious example of where there's non-musical communication is this work from Georgia Tech, which has been going for several years. It's called Shimon. It's a robot improviser, and you can see it has a head, or kind of a head-like object that nods up and down in time with the music, and it helps give the performers, the human performers, a sense of presence of the AI that's in there. All right, so let's talk about the experimental design for our work. So we have two phases. The first phase is a training phase. We have a percussionist, and the percussionist is playing a drum kit. It's a special kind of drum kit. It's a digital drum kit that captures MIDI information about the performance. That's digital information about where the drummer is striking each drum and how hard they're striking, and if they're gripping the cymbal or letting it go, and so on. We also have an instrumentalist, in this case playing a clarinet, who's just playing into a microphone, but they're also wearing a biometric sensor. Then in the second phase, the evaluation phase, we swap out the human drummer for an artificial intelligence represented by the screen that you can see there. We still have the instrumentalist. We have the AI improviser. The instrumentalist is still wearing the biometric sensor and playing into a microphone. So the drum kit we used, I'm not trying to do an ad for Roland, but it's a pretty amazing kit. It captures at very high fidelity all of the nuanced information that the percussionist provides into the system in digital form, and that can be converted symbolically into tokens that we use to train our neural network. So in the training phase, here's a schematic diagram of what we did. We've got the instrumentalist and the percussionist, and we're taking data from the biometrics of the instrumentalists and also the audio data of what they're playing. We're taking digital performance data from the percussionists. We're feeding that into a system that basically converts the audio information to pitch information, because the instrument's monophonic, it's fairly easy to do. Converting that to MIDI, doing some processing, and using that to train a convolutional neural network. So I'll talk about the neural network in a bit more detail. We used a temporal convolutional neural network, and we trained it on about 3.5 hours of performance data. So several different musicians using different instruments and different drummers. We used high-resolution MIDI capture using the drum kit that I showed there before, and pitch to MIDI. MIDI is traditionally, it's a very old protocol for sending musical information. The drum kit actually sends it in a high resolution by basically cheating a bit on the MIDI standard and sending very high resolution information. For the purposes of expediency, we decided to quantize all of the timing information to 12 time steps per beat. And the TCN system is a token-based system. So these deep learning neural networks are based on language translation models. So we need to convert musical information into a series of tokens. So we have tokens that represent things like the note starting, the note is sustained, velocity ranges, and so on. We concatenate this with the notes from the instrumentalist, and that yields 1,639 unique tokens, which we reduced to 451 by removing any token that was used less than 20 times in all of the performance data. And that was approximately 1,100 tokens. Now, the biometric data capture was done using an Empatica E4 wristband, and that measured skin conductivity and also heart rate. It ended up we didn't really make use of the heart rate data. We just focused on skin conductivity because prior research had shown that it was quite a useful measure of indicating flow in music performance. The skin conductivity was normalized and then converted into 3 ranges, and those 3 ranges are expressed as tokens. And we trained the TCN model to predict a combination of notes played in any given measure of performance based on both the musical and the biometric data from the 3 measures that preceded it. So here's a diagram, or simplified diagram of the neural network. Along the bottom you can see 3 measures of music information, the skin conductivity information, and also a mask that's provided on the last measure, which basically encourages the neural network to try and predict what that last measure is. And this goes through many different layers and eventually comes out with a target sequence. So on a measure by measure basis, it's predicting what the most appropriate tokens are to convert to music to play. And you can imagine this moving along like a sliding window. So every measure, everything just shifts across to the left. So we trained the system on an NVIDIA DGX1, which is just a big set of GPUs, and achieved a perplexity of 6.7. If you're not into deep learning, this is a reasonable result. It basically says that the system finds an average of 6.7 tokens most likely to occur at the next point from the 451 tokens that it knows. Interestingly, if we replaced the skin conductivity information with just a null token, a start token to signify the start of the measure, we got basically the same perplexity measure, which indicates that the biometric data didn't really assist or impede training of the network. And I'll return to that point at the end of the talk. Okay, so that's the network training phase. The important thing is the communication between the AI and the human musician, and that's done through a visualisation of confidence. So basically, the TCN, we added a softmax layer that gives you a probability measure for each of the 2.5 by 10 to the 127 possible output tokens that are possible for each measure. And those tokens are decoded into MIDI messages and sent to the Roland drum machine, which is also a drum synthesizer. It's the same synthesizer that the percussionists used to play in the training phase. And in addition, this softmax layer gives you a probability range every 500 milliseconds, which is how likely it is to play those notes. And we use that information to create a confidence measure that we communicate to the human performer. And I'll go through how this animated icon works. We deliberately chose something that wasn't particularly anthropomorphic, so not human-looking, but kind of iconic. When the AI lacks confidence, it frowns and doesn't make eye contact with the performer. If it's enjoying the performance and getting more confident about what it's predicting, it starts to smile. If you can keep it sustained in terms of its confidence for 4 bars, it starts radiating and glowing. Okay, so does it work? So we tested this through some evaluation. So we replaced, as I said earlier, the human drummer with the AI drummer. We had pretty much the same setup, capturing biometric information and note information from the instrumentalist. That was fed through the neural network, but this time, of course, the network was doing the prediction. And the output is MIDI data that goes to the drum to actually play the drums, and also a confidence measure and timing information. So you may have noticed that the emoticon was kind of bouncing up and down in time with the music. So it would try and keep time, which is a common thing that musicians do, particularly if they're playing with people who aren't very good. Okay, so what happened when we did the evaluation? Well, we got 7 experienced musicians, 3 women and 4 men, aged between 18 and 56, and they participated in a number of improvisational sessions with the AI, giving us a total of 28 trials. Each session was fairly short, about 3 to 4 minutes long, and we got participants following each session to report on their measure of flow using the FSS2 short questionnaire. The details are in the paper if you're interested. So we tested 3 different conditions. The first condition was a truthful communication between the AI and the performer, so it would be smiling when it was confident and frowning when it wasn't. Inverted deceptive, so it would actually be smiling when it was not confident and frowning when it was confident, and basically by removing the facial features and just having the blob bouncing up and down to keep timing with the expression removed. And we also did the same for the biometric information. So the results that we got indicated a slight favour towards the flow being increased through the truthful condition. We performed some additional statistical analysis and matched pair t-test and found that really at the 99% level, it improves it by about 0.5 on a 5-scale rating. So musicians experienced more flow using the confidence visualisation with a reasonable degree of certainty for the musicians that we tested. So in addition to that, we also did a listener evaluation and asked the question, can audiences differentiate between the results played by the system? So we created 16 tracks from 6 sessions. We had truthful and deceptive visualisation conditions that were randomised, and then we selected 6 tracks with stratified sampling, so people didn't know if they were random or, if they were truthful or deceptive. But there was an equal number of both, and 100 participants were recruited on Mechanical Turk and asked to make A/B comparisons. Which performances were more interesting, which performance gave a better musical balance between drums and the saxophone, as that was the instrument that was used. And we discarded, I think, 4 of the 100, so I think there's 96 evaluations that were done. The 4 were discarded because we found that they weren't actually listening to the music. And you can see that in total that there's a reasonable balance towards the truthful indication in terms of musicality. So I've got just a quick sample. This is the truthful condition. And this is the deceptive. There's links in the paper, you can listen to all of the tracks. So a very quick evaluation of the results. I think we demonstrated that using this form of communication definitely supports the hypothesis of communicating the internal state of the AI to the human does increase their ability to experience flow and give a better performance. The results from the biometric measures were inconclusive. They didn't statistically work out one way or the other. And we think one of the reasons for this was that there's a lot of movement. When you're playing an instrument and you're wearing a wristband, there's a lot of movement that corrupts the signal. So there's a huge amount of noise in the signal that was coming off. And in other studies, people have resorted to things like strapping sensors to people's legs and telling them not to move their leg, which, for musicians who like to tap and move their body is quite difficult. So I think that's something that needs more work and probably better quality sensors that are immune to that kind of movement that you get when someone is really getting into a musical performance. So we're also looking at expanding the AI improviser, and we've now got about 50 hours of training data, and the quality is much better. I'll just finish off with a quick video, and you can well, the video will explain it. You can get the sense of what people were doing.
When performing musicians improvise together, they make use of non-musical cues and communication to keep things flowing. When humans perform with each other, this is a natural and intuitive process. But what happens if one of the performers isn't human? We trained a neural network drummer to improvise with human musicians and explored bi-directional communication between human and machine performers. The AI improviser communicated its confidence in the performance using a simple animated emoticon. When the AI lacks confidence, it avoids eye contact and frowns. When confident, it looks at the human performer and smiles. Sustained confidence causes the emoticon to glow. We communicated the human performer's state to the AI by measuring skin conductivity during the performance. Our results showed that communication from machine to human improves the human player's flow and the quality of the improvisations. The communication from human to machine results were inconclusive, and more research is needed to establish effective human-to-machine communication. Our aim is to build AI systems that are active and responsive players in improvised musical performances with human musicians.
Okay, thank you very much.
We only have time for maybe 1 or 2 questions. Raise your hand.
Well, Emily Barakova from Eindhoven University of Technology. So electrodermal activity has something about the arousal, but not about the valence. So the electrodermal signal could signal that the person is angry, not happy.
Yes, that's true. It's not a perfect proxy. We based using that measure on a large-scale study that was done a couple of years ago with a large number of improvising musicians, and it found that there was a correlation between being in a flow state and being in changes in skin conductivity. So, but yeah, it's an imperfect measure. We have looked at other measures, like looking at facial features, for example, trying to do some machine learning on that. But most people have like jazz faces, which correlates to just looking disgusted if you put them through a standard kind of neural net analysis. So I think it's something that does need more work, probably at the psychophysiological level, to really understand further.
Unfortunately, we have to move to the next speaker. Our speaker will be around if you want to talk more after.